Alright, this video contains the solutions for your Semester 1 exam review. I'm going to go through all the solutions to the problem. I would encourage you to fast forward and pause and use the video. You don't just have to sit there and watch the whole video. Just look at the parts that you need. If you're working on a difficult problem and the video gets you to a point where you feel like, oh, that's the thing I was missing, then pause the video. Don't watch the rest of it until you try it yourself. Try to make the video work for you. Okay? Now, some unit conversions. So 53 millimeters, and I want to convert that to nanometers. Now, this is the way I do it. You may have learned, perhaps in chemistry class, a different way of doing it, and I'll show you my way. So I'm going to go 53 millimeters, and I know milli means 10 to the negative 3 meters. And then I want to convert the meters to nanometers. And I know that nano means 10 to the negative 9. Alright, so those cancel, these cancel, and that'll give me my correct units. So I'll enter that in my calculator. Let's see if I can get you to, so you can see that. That looks good. So that's 53 times 10 to the negative 3 divided by 10 to the negative 9. Oops, and it looks like I messed up the syntax there. So let's see, what did I do? Oh, I forgot the, let's try that again. 10 to the negative 9, that looks better. And then if you want your calculator, you can set your calculator if you want to scientific notation mode. Hit the mode button to do that. And then go back to the regular screen and hit enter again, and then it will tell me 5.3 times 10 to the 7th. Okay, and then units would be nanometers. You can't write your answer with that E. That's calculator speak. All right. Okay, I'm going to go through the rest of them a little bit faster than that. So I've got 25 kilometers. I want to get rid of the kilometers. I'm going to turn that into meters first. Kilo is 10 to the 3. And then I want to get rid of the meters and turn that into gigameters. And giga, 10 to the 9th. So I've got 25 times 10 to the 3rd divided by 10 to the 9th. And in scientific notation mode, 2.5 times 10 to the negative 5 gigameters. And here I've got 1.3 kilograms. Don't want kilograms. Kilo means 10 to the 3rd. I want the grams to cancel, and I want micrograms, and micro means 10 to the negative 6. So, looks like I've got 1.3 times 10 to the 3rd divided by 10 to the negative 6. Oops, there's that same mistake I made last time. There we go. 1.3 times 10 to the 9th micrograms. I've got 40 centimeters to meters. That's an easy one. That's 0.40 meters. 10 to the 7th seconds to years. So this isn't just a conversion, metric conversion. This is a full-on unit conversion here. So I've got 10 to the 7th seconds. And I know that seconds, I want to change seconds to, let's say, hours first. If you know that conversion, there's 3,600 seconds. And an hour, that's 60 times 60. And then I don't want hours. I don't know how many hours there are in a year, so I'm going to go 24 hours is the same as 1 day. Then I know there are Notice I'm always putting these top and bottom so they cancel. That there are 365 days in 1 year. If you want to do 365.25 for the leap year, it doesn't matter. I don't care about that. So let's see what we got here. We got 10 to the 7th divided by 3600 divided by 24 divided by 365. That is 3.17 times 10 to the negative 1 years, or about a third of a year. Okie dokie. Meters per second to miles per hour, and given that conversion, so I've got 65 meters per second. So I want miles per hour, so let's get rid of the meters first. I know that there's 1,609 meters in 1 mile. Oh, that's good. And now seconds. I know that there are 3,600 seconds in 1 hour. So looks like I've got 65 divided by 1609 times 3,600, about 145 miles per hour. That's fast. And then square conversions, you just have to remember to square the conversion factors. So 5 square meters, well, I know that if I want to go from meters to centimeters, that centi is 10 to the negative 2, but I am square units, so that means I have to also square the conversion factor. So that means I have 5 divided by 10 to the negative 2. Let me go back and let me put that in parentheses. It's at the bottom of that fraction. 10 to the negative 2 squared. And that gives me 5 times 10 to the 4th square centimeters. Okay, there's your conversions. You can practice those. There'll be a couple of those on the test. And these can also, you know, that converting from meters to kilometers, things like that, centimeters to meters, that comes up in problems all the time. What's the SI unit for mass? That is the kilogram, not the gram, the kilogram, time, seconds, and length, meters. That's the one that trips people up most, right? And I think that it maybe is the gram, but it's not. It is the kilogram. Following table gives lengths in inches of particular spring as it is stretched by various attached weights, and the weights are given in pounds. So, oh, looks like they're not given in pounds. Looks like, sorry about that, looks like they're given in newtons. So, scratch that. So why should weight be graphed on the horizontal axis? Well, if we were doing this experiment, I think we would control this, the weight, and the length would depend on that. So I would say something here like, because we control, it's our control variable is the weight. That's our independent variable. All right, I'm going to flip back and forth here. So on the horizontal axis, I have weight. So this is going to be a graph of length versus weight. Don't forget that label up top. Weight here is going to be length here. This is measured in meters, and this is measured in newtons. And here for the weight, I'm going from 1 to 5. So let's see if I did, what about every 5? That could be like 1, 2, 3, 4, 5. That looks pretty good there, nice and spread out. Just be careful, make sure you do 5 each time. If you did 5 and then 4, that would be a mistake in scaling. And then on the vertical axis, looks like I'm going up to 0.86. So let's see, 1, 2, 3, 4, 5, 6. So if I made each one of these, that's 16 there. So if I made this like 0.1, 0.2, it looks like I've got enough room to do that. This is not the only way you could scale this. I think it's a pretty good way. Actually, my 0.86, the last one's just going to be a hair above that, right? Because these will be like halfways. That'd be like 0.75, right? Okay, so let's see what we got. We got 1.27. 1.27 would be about there. And I've got 2.4. 2.4. I've got 3.56. Oops, that's no good. This would be 0.55, right? So it'd be just a little bit above that. That's better. And then sorry, that was 3.56, wasn't it? Oh dear, I missed that too, didn't I? That's 2.8, so sorry about that. Of course, that's why we do these in pencil. Can erase. And 4, 0.73, about there. And 5, this would be 0.85, so it'd just be a hair above that. And then with a straight edge, this piece of paper I have here, I want to draw our line of best fit. I want to try to go somewhere like kind of between the points. So some are above, some are below. That looks all right. Okay, that's a decent looking graph there. Find the equation for the line and show the work. So let's see, I need the slope. Let's see, what points should I use? I'll go ahead and use this. That looks pretty close to going right through there. And that looks good too. Try to pick 2 that are fairly spread out, not points from the data table. Alright, so what do I have here? I've got the point, this would be 1.2, comma 0.3, and then I've got 3.6, comma 0.65. So my slope as rise over run, that'd be 0.65 minus 0.3. It's rise over run, 3.6 minus 1.2. It's 0.35 over 2.4. And then jam that into the calculator. 0.35 divided by 2.4 is, I'll get out of scientific notation mode. Let's say 0.15. It's about 0.15. And the units of the slope, rise over run, would be meters or Newton. Right? Okay. Now, I need to find the y-intercept. So, using the model y equals mx plus b, and using either one of those points, I'll go ahead and use this one. There's my y equals m that I just found, x plus b. So solving for b, that gives me 0.65 minus 0.15 times 3.6 is about 0.11, and that looks pretty good, consistent with my graph there. And that's the y-intercept, so that'd be in meters. So my equation is y, but y is length, right? So length equals the slope, which is 0.15 meters for every 1 Newton, times x, which is weight, plus my y-intercept, 0.11 meters. There's the equation for my line. Don't give me no y's and x's here, right? I'm going to use the quantities that we're working with. What's the meaning of the slope of the line? Well, the slope means for every 1 Newton of weight, the spring stretches 0.15 meters. Right? We read our slopes from the bottom up, just like that, just like you do in your lab reports. Explain the meaning of the y-intercept. Well, let's think about that for a minute. When there's no weight, the spring still seems to have a length of 0.11. So I'm going to say that that 0.11 meters, what makes sense is that's the relaxed length of the spring when there's no weight hanging on it. There's different ways of saying that I think would be fine. What's the relaxed length of the spring? Now, according to our model, how long would the spring be if you hung 10 newtons on it? Well, that's a weight, right? So plugging that in, I can't read it from the graph. My graph doesn't go that far, but I can just use my equation. So length equals 0.15 meters for every 1 Newton times 10 newtons plus 0.11 meters. So here I'd multiply that by 10, that would be 1.5 plus 0.11, so that'd be 1.61 meters. Do that in your calculator, of course. See how the newtons cancel out there? We get meters. All right, that was fun. Bet there'll be some graphing problem like that on the exam. All right, so let's see. In part A, for each one of these, we want to describe, using a clear, complete sentence, how the motion, not the graph shape, of object 2 differs from the motion of object 1. And B, we're doing the graph of velocity versus time for each one. And in the space provided here, we're going to draw motion maps. So these probably look familiar. You saw these problems on a test earlier in the year. So let's see if we can make sense here. We know that the slope of a position versus time graph is velocity, and this is steeper. So that means object 2 is going faster. But you can see here they both start at the same place. So I'm going to say that the objects start at the same position, but 2 is faster. And maybe I should also say that they're both in the positive direction. They're both moving forward, right? They both have positive slopes. So let's see, the slope of object 2 is, they're both going at a constant velocity, right? Sorry, those are supposed to be horizontal. I hope they look horizontal enough. Looks like they're going up a little bit. Those are supposed to be horizontal. And 2 is faster. But they're both positive, so something like that. Now let's see, my motion maps, they both start at time at the first tick of the clock. They're both at 0. And then object 2 goes faster, which means there's more space between those, where object 1 will do something like that. So you don't need more dots than about 3 to get that across. So something like that. Tick, right? This is time 0, 1, 2, 0, 1, 2. Right? How about this one? Looks like object 1 starts at the origin and moves forward, just like it did here, but object 2 starts at a positive position and moves backwards. You can see they cross each other. They're at the same position here. So let's see, how should we say that? Object 1 moves forward from the origin. Object 2 moves backward from a positive starting position. And it's, I think, worth noting also that this is steeper than this, so we would say object 1 is going faster. Not because it's positive, because it's steeper, right? And this one's going backward, but at a slower, it's a less steep. So object 2 is slower. Something like that. So object 1 has a positive constant velocity. Object 2 has a negative constant velocity, but it's not going as fast, so it should be closer to 0, right? Its magnitude should be smaller. So something like that. Now let's see if we can get this. I'm going to make my object 1 look like this. It's the faster one. It's going forward. It starts at the origin. Now this object starts ahead, let's say here, and moves backwards, not as fast. So maybe something like this. And if you look at the time clicks, here's 0, 1, 2, 0, 1, 2. You can see at time 1 they're at the same place. So that would be like our time 1 there. Right, so something like that. It is definitely important here that they go opposite directions, that these arrows and spacings are bigger than this one, and that this one starts up here and goes backward. Those are the details that are important there. All right, here we've got a velocity versus time graph. So this is something, let's just think about what's going on here. For 8 seconds, it's going at a constant velocity of 10, right, moving forward at 10 meters per second. And then for 10 seconds, it's going backwards at negative 5 meters per second in the negative direction. And then it looks like for about 4 seconds here, it stays still. And then here, for the last 2 seconds, it has a positive velocity of 5 meters per second. Okay, we're supposed to construct a position versus time graph. Now these, the velocities, these are the slopes. So if we think about our position versus time graph here, position in meters, time in seconds. These are the slopes. So I want a graph that has a slope of 10 and then a slope of negative 5 and so on. You could also think about it in terms of how far this thing goes. If it's going 10 meters per second for 8 seconds, 10 meters per second for 8 seconds, and how far is it going to go? Well, that's just the area of this, right? That's 80 meters. And then here, going backwards at negative 5 for 10 seconds. So this area here, you say this is 50 meters, and it's going backwards, so it's like negative 50, right? And then here, this is just 0, it's not going anywhere. And here for 2 seconds, it's going 5 meters per second. So that would be 5 times 2, or 10 meters there. Those are those little areas. So there's another way we could think about it. So here, if I do 1, 2, 3, 4, 5, 6, 7, 8, if this is 8 seconds right here, and we did, let's see, how about 10, 20, 30, 40, 50, 60, 70, 80. If I make this 80. Again, this is not the only way to scale this. I think it's probably pretty good scale. So after 8 seconds, it's gone 80 meters if we start from here. Now, it didn't tell us where we started, so you could actually, oh no, sorry, it says assume a position of 0 at time 0. So we do have to start there. If it didn't say that, then we wouldn't really have any way of knowing. So you could start anywhere, but the shape of your graph would be exactly the same. So I know that in the first 8 seconds, it goes 80 meters. So it would look like that. And then from 8 to 18, so let's see, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It goes back 50 meters. So if you go forward 80 and then back 50, it's going to leave you at 30, right? So, oops, there we go. So that looks like that. And then for 4 seconds, from 18, 19, 20, 21, 22, it doesn't go anywhere. And then for the last 2 seconds, 23, 24, here, it goes forward 10. Right now it's at 30, so that would be at 40. So there's our position versus time graph, right? We're working from having velocities to creating this graph. What's the average velocity for the entire trip? Well, I will give you this equation. Average velocity is equal to displacement divided by time. So, how far, what's its displacement? Displacement is the difference between where you start and where you end. So it started at 0, ended up at positive 40. That's a displacement of positive 40, right? I started at 0 and ended up at positive 40. That's positive 40. How long did it take? Like a total of 24 seconds. So that's 1.7 meters per second. There's our average velocity. Average speed, well, that's a little different. That's total distance divided by time. So that takes into account everything that happens in between. So let's look at our total distance. Our total distance, we went 80 and then 50 and then 10. So total distance doesn't care about the signs. So I went 80 and then 50 and then 10. That's 80 plus 50, forget the negative. 80 plus 50 is 130 plus 10 is 140. So that's 140 meters of total distance divided by 24 seconds. And that is 5.8. All right. It's another constant velocity type problem. So I got two toy cars initially 12 meters apart, and they're going to move toward each other at the speeds shown. Make and label a quantitative graph of the motion of the two cars. So position versus time. Let's see, our position, they start at 12 meters apart, so let's see. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, perfect. There's 12. It's not the only way to scale it, but that fit nicely there. Time, I don't know, let's see. I guess we could kind of ballpark that, but I don't think it's going to take too long for them to run into each other. I'll make this, say, I don't know, maybe about 5 seconds. So, let's see if I did 1, 2, 3, 4, that almost fits. Maybe you'll make it like 4s, like this. 1, 2, 3, 4, 5. That's time in seconds. This is a position versus time graph. Did I do that in my last one? I'm thinking maybe I forgot. Oh, I did. So you never know when your annoying physics teacher might take a point off for that. So let's try to remember to label our graphs. Okay, so car A starts at position 0, and it's going forward at this velocity, so that's its slope. Now that's kind of a funky, I could try to put the 1.4 in here. What I'm going to do is find an easier point to plot. I'm going to say, what about like 5 seconds later? 5 is a nice number here because that's going to make this into a easier to deal with number. So 1.4 meters per second times 5 seconds later, it will be at 7 meters. So 5 seconds later, it's going to be at 7 meters. You could try to plot more points. That would be totally fine. That's just an easy way of dealing with that. You'll have a straight edge, but I draw that nice and straight. All right, and then here I'll do the same thing. This one starts at 12, right? It starts at 12, and it's going to go backwards, downward slope. 2.2, let's see where that's going to be at 5 seconds later. It's going to go 11, but it's going backwards, so that'd be from 12 all the way down to 1. And let's see how straight I can get that. Not very straight. So something like that. So they intersect somewhere here, right? Okay, that looks good. Now, write the mathematical models that describe the motions of cars A and B. That just means the equations of these lines. So the position of car A is, let's see, what's the equation for this line? It has a slope of 1.4 meters per second times time plus a y-intercept of 0 meters. You don't have to put that there if you want, but I'm just going to put it there so I can see. That's the y-intercept. And then the position of car B is, let's see, that has a negative slope of 2.2 meters per second times time plus y-intercept of positive 12 meters. And then where and when do the cars collide? Show the algebra. Well, look, if when they collide, they're at the same position. So just set those two equal to each other. So 1.4t would be equal to negative 2.2t plus 12. 3.6t, I'm adding that over to that side. So they would intersect at time uh, 12 divided by 3.6. It's about 3.3 seconds. And then you can plug that into either one of these to figure out where that happens. You should get the same thing, just about 3.3 times 4 is about at 4.6 meters or so. And we can check with our graph and see if that looks about right. 3.3 and 4.6. That looks pretty good. Right? And here we have a velocity versus time graph for object A. This is 0 here. I'm just going to not trace over that. You can see that's my 0 there. Describe the motion of object A. Now this is velocity versus time. So this thing starts with a positive velocity of 10, and then the velocity gets smaller. Here it has a velocity of 0, and then it goes into negative. So it looks like it's moving forward and slowing down until it has a velocity of 0, and then it starts going backwards faster and faster. So we'll try to say something like that. So it starts with positive velocity of 10 meters per second. It turns around after 2 seconds, and then goes, let's say, and then it speeds up in the negative direction. So by the time after 10 seconds it's going like negative 40 meters per second, right? It's like 80 miles an hour in the negative direction. Right? Okay, so can we write a mathematical equation for the velocity of this? That's the equation for that line. So this is velocity versus time. So we're thinking like y equals mx plus b. So velocity is equal to the slope of this. Let's see, rise over run. Looks like the rise, it's going down 10 over 2. So the slope of this line is negative 5. The units, meters per second. That makes sense. The slope of velocity is acceleration times time, that's my y, equals mx plus the intercept was 10 meters per second. Determine the object's average velocity between time 0 and time 10. I'm actually going to do this first. Determine the object's displacement from time 0 to time 10. I'm going to do that first because then I can do average velocity is equal to displacement divided by time. So if I have the displacement, then I can do that, right? So here, remember that displacement is equal to the area here. So it'll be this triangle here. That has 1/2 base times height. That would be positive 10 meters right there. And then I've got a big old negative triangle here that's all underneath the time axis. This triangle here. That has a base of 8, right, from 2 to 10. It's 8 and a height of 40. So 1/2 base times height, I think it's 160, but it's underneath, so that's negative, right? That's going in the negative direction. These are all negative velocities. So my displacement, what's your displacement if you go forward 10 and then back 160? That's back 150, right? And then, let's say here, well, that's negative 150 divided by a total of 10 seconds. That's negative 15 meters per second. All right. That's an important concept that if you've got a velocity versus time graph, these areas give you the displacement. It's an important concept. Here we've got an object dropped off a 100-meter tower. That means the acceleration is negative 10 meters per second How fast is the object traveling after 2.5 seconds? Well, you could use an equation here. So you could use this one. You'll have that equation for the exam, right? You can also just think about it, right? I mean, if it does this for 2.5 seconds, it has negative 10, then negative 20, and then it'd be negative 25 after the half second. So either way, plug stuff in here. If you're going to use this, final velocity is equal to acceleration times time plus we dropped it, right? If we drop it, then the initial velocity is 0. So one way or another, you should get that it's negative 25 meters per second. How far does the car travel in those 2.5 seconds? Car, well, that's weird. An object is dropped off a 100-meter tower. Now we're talking a car. I think should say object. That's bad cutting and pasting by your teacher there. So how far does the object travel in the first 2.5 seconds? So looking at our equations, I think that we know, well, let's write down what we know first before we pick that. We know that acceleration is negative 10. We know that the time is 2.5 seconds. We know that our initial velocity is 0 because we're dropping it. So looking at our equations, I think that we want this one. And since we're dropping things, I'm going to call it delta y instead of delta x. You're not going to lose any points for that if you call it delta x, but it's a little bit more clear. So I'm going to use this equation, delta y. Please, on the exam, you want to write down the equation that you're going to use because I'm going to give you points for having the right equation, even if you mess up after that. And then my initial velocity is 0, so that's going to go away. So let's see. Entering that into my calculator, get delta y is negative 31.25 meters. That's the displacement. Now this says how far. I could get like really fussy on you here and say how far. Nobody ever answers the question how far with a negative number. That just doesn't happen. So how far really means distance. So I'm not going to take off points, but really if you say how far, you'd say, well, it went 31.25 meters down, and you'd leave the negative off. But I'm just going to leave my answer like that. We're not going to get fussy about that. And we know that means down. Right? Now, what would these look like? Again, I apologize here. I think that should probably be a y since this is being dropped, right? Instead of x. So it's being dropped, and here that means the velocity is going to get more and more negative. So I think I need to move this axis up to here, right? So I can do this kind of thing. It can start at 0 and then go down like this. And the slope of this would be the acceleration. And here, it starts at a position of 100, and it's dropped. So, look like that. Right? It starts off with a slope of 0, and then the slopes get steeper and steeper to match that. Okay? Number 16, you get an elevator on the first floor of a tall building. During the first 2 seconds, the elevator accelerates to 2 meters per second. So this is velocity in meters per second, time in seconds. So during the first 2 seconds, the elevator accelerates to 2 meters per second. Like that. And the elevator maintains a constant velocity for 6 seconds. So it'll be like 3, 4, 5, 6, 7, 8. Constant velocity. Jeez. All right, this is a velocity versus time graph, so constant velocity looks like that. And then decelerates to a stop during the final 2 seconds. So that's going to look like that. How far did you travel in the elevator? There's a couple ways to do this, but I think by far the easiest way, that way that we talked about the most, if you have a velocity time graph, if you find the total area here, that's going to tell us how far we went. So we've got an area of a triangle here. So 1/2 base times height plus big rectangle, that's 6 by 2, plus another one of those same triangles. So that's like 2 plus 12 plus 2, that's 16 meters. Okay. You could do it saying, okay, this is a constant acceleration, and you could use our kinematics equations, like these type of equations, saying, okay, my initial velocity is 0, my acceleration is 2, this acceleration is the slope of that, and the acceleration here would be 1 meter per second would be the slope of that, right? And so on. Then you could say here, there's 6 seconds of constant velocity, and work it out that way. I think that's more difficult, but if that makes more sense to you, you can use those equations. Just understand here you've got acceleration, and then constant velocity, and then acceleration. So you'd have to break it into different problems. So let's see. Here we've got a position versus time graph. This position versus time here has a constant slope. That means it's a constant velocity, and it's negative. So negative like this. And then it starts to get steeper and steeper in the negative direction. So from here it gets even more negative. Right, the slopes get even more negative. Acceleration is the slope of velocity. The slope of that, well, that's 0. And then the slope of this, well, that's some negative number. That would look like that. Here, let's see. Here's something that's curving upward. It starts with looks like a slope of 0, and then gets up to some kind of steep slope here, and then it gets less steep back to 0. So that'll look like this. Keep in mind here, if you're wondering, if you're thinking to yourself you're going to make that look kind of like this but curved, we have not dealt with anything where velocity versus time graphs are curved. That would be varying acceleration. So we have not dealt with that, and we're not going to deal with that. So we're expecting our velocity versus time graphs will either be horizontal lines or lines with constant slope, right? No curves here. And then acceleration, I've got a positive slope and negative slope. And by the same token, that means that our acceleration versus time graph is going to be always bits of horizontal lines. Just got to get them in the right place. All right. Draw a qualitative force diagram. Qualitative, it just means get it, the basic idea. I don't need any numbers. A box pushed across a rough floor at a constant velocity. constant velocity means balanced forces. So I would have my force of gravity on the box from the Earth. I would have the normal force on the box from the across a floor. Floor. Those would be balancing each other out. It's being pushed, so there's the force, the push on the box from, I guess, the pusher, whoever is pushing it, person if you want, or whatever. And then it's moving at constant velocity. It says rough floor here to suggest that there is friction on the box also from the floor. And those are also equal. We've seen diagrams like that before. How about a book sliding down a frictionless ramp at a constant velocity? Well, that's impossible. If there's no friction, it's not going at a constant velocity. So let's see, how shall we fix that? Well, we can either say that it's not going at a, let's do two. We'll do not constant velocity, or in other words, no friction. Let's do both. So what would that look like? If this is my ramp, then of course gravity is straight down, and the normal force. And actually, let's break this up first. So drop that straight down. Remember how we do this? We can tilt that and then drop this straight down, and this straight over parallel to the ramp. That's my 90-degree angle. And then I know whatever's going on here, this balances the normal force. Right? And that's it. These two balance, and then this part of gravity right here, that's what's going to accelerate it down the ramp. There is no force here. There's no other force. Part of gravity is down the ramp. All right, and then if there was friction, so then let's draw it with friction at a constant velocity. Then it would look just like this, just like our last one. Break that up in exactly the same way. The normal force is still going to balance that. But now this little piece here is going to be balanced by the force of friction. There's our normal force, there's gravity, and this little piece right here is going to balance with that. So there's really three forces: gravity, normal force, and friction. But gravity breaks up into those two components. One balances the normal force, one balances friction. That's really how it happens. So I guess we'll make the most of my mistake there. At least we got two diagrams out of that, right? All right. Let's see, you got two blocks of masses 5 and 2. 5 and 2 pushed across a frictionless surface by a force of 3 newtons. There's that force right there. I'm going through this lead pretty fast here. 1 second. All right. I draw quantitative force diagrams for the blocks. It means with numbers. So for block 1, block 2, block 1, force of gravity. Block 1's 5 kilograms, so it'd be 50 newtons of gravity. And the normal force will balance that. Now look, the push is on block 1. This force is not on this one, right? If there's like a hand pushing this thing here, it's pushing on this block. So that's my 3 Newton force applied to M1. 3 newtons, that's the force of the push. Okay, there's no friction. But there is an interaction here between these two, right? So there will be, those are equal by the way, there will be a force backward here. I'm trying to make it smaller than that. I'm trying to make it look smaller. This is the force of block 2 on block 1, right? I mean, that's bumping into this. They're in contact with each other, so there is a force. This will push back on this. And then on block 2, we've got 20 newtons and 20 newtons gravity and normal force, because it's 2 kilograms. Those are equal to each other. And this is the kind of thing that is just screaming Newton's third law, right? Equal opposite. So if this pushes back here, then block 1 is going to push forward on this one, right? That's how that one moves forward. And that's our equal opposite Newton's third law pair. Sorry, I made them so small and tiny little 3 lines there to show that they're equal. Right? Okay, now find the acceleration of the blocks. So let's write my unbalanced force on this one is the force of the push minus the force of 2 on 1. So, and then let me write the unbalanced force equation for this one too. This one is just, these cancel out, it's only this. That's the force of 1 on 2. Okay? Unbalanced force is equal to mass times acceleration, right? Mass of this block is 5, equal to the force of the push minus force of 2 on 1. And then here, mass times acceleration equal to the force of 1 on 2. But we know that these are equal opposite, right? These are equal to each other. So just like with the Atwood's machine, when the tensions cancel out, when we add these together, I add these together, I get 5a plus 2a, and 7a equals 3, and then minus, those cancel out. So the acceleration is 3/7, or about 0.42 meters per second squared. Cool. If the blocks have an initial velocity of 5 meters per second, how long will it take them to travel 10 meters? Okay, so that's like kinematic stuff, right? So an initial velocity of 5 meters per second, we want them to go 10 meters, and we know the acceleration, we just found that is 0.42, right? And we want to know how long. So that looks like this equation.